All right, welcome to The Explainer. Today, we're going to talk about something you've probably seen 1,000 times, but maybe never really thought about: the transformer. It's that quiet, unassuming box that, no joke, powers our entire world. And we're about to figure out the invisible magic that makes it all work. So here's the big question, the central mystery. Think about it for a second. You have two wires that aren't touching. Power goes into one, and then somehow it just appears in the other, jumping across an empty space. How on earth is that possible? It sounds like magic, right? Well, that's the puzzle we're going to solve. The secret, as it turns out, isn't quite magic, but it's close. It's an invisible force field, magnetism. And it's all wrangled and controlled by this incredible device right here, the transformer. This is the heart of the whole operation, and we're going to take it apart, piece by piece, starting with what it's doing when it's just sitting there. Okay, first things first. Let's imagine our transformer is plugged in, it's got power, but we haven't actually connected anything to it. It's just waiting. In the engineering world, this is what they call the no-load condition. So what you're looking at here is our transformer in that exact idle state. On the left, you've got the primary winding. That's where the power comes in. On the right, the secondary. That's where power is supposed to go out. But notice, the circuit on the right is open. It's not connected to anything. That means the secondary current, let's call it I2, is zero, zilch. No power is actually being delivered. But here's where it gets interesting. Even though it isn't doing any work, it's not totally off. It's still sipping a tiny bit of current just to stay energized and ready to go. You know, it's kind of like a car's engine idling at a stoplight. It's running, it's burning a little fuel, but it's not actually moving the car. That's exactly what this no-load current, or I.O., is doing. So what's this little idle current actually for? Well, it's multitasking. It's got two main jobs. The first part, the magnetizing component, or IM, has one very important purpose: to build and maintain that magnetic field inside the transformer's core. Then you have the second part, the working component, or IW, which basically covers the small amount of energy that gets lost as heat inside that core. And this is a great way to visualize how those two jobs relate to each other. It's called a phasor diagram, which is really just a fancy engineer's map for electrical forces. See the horizontal arrow, IM? That's our magnetizing current. And the vertical one, IW, is the working current. The key thing is they're not pulling in the same direction. The total no-load current, IO, is the combined result of both of them. Now, don't let the formulas scare you. If that diagram was the map, think of these as the precise GPS coordinates. This is just the math that proves the map is accurate. You don't need to memorize any of this. The big takeaway is just that engineers can predict exactly how these currents behave. All right, our transformer has been idling long enough. Let's put this thing to work. It's time to see what happens when we flip the switch and actually connect something to it, when we put it on load. Here we've got a perfect before and after. On the left, there's our familiar idling transformer, but on the right, boom, we've connected a load. Now, this could be anything: a light bulb, your laptop, the whole neighborhood. The important part is the circuit is now complete, which means current, our friend I2, can finally start flowing out of that secondary side. And this, right here, is the brilliant part. The second that I2 current starts to flow, it creates its own magnetic field. And this new field pushes back against the original one. Now, the laws of physics demand balance. So this pushback is like a signal, a message sent back to the primary side saying, hey, we need more power over here. So how does the primary side respond? It starts pulling an extra amount of current from the source to match the demand. We'll call this extra current I1 prime. And here's the thing: this new current is a direct reflection of the load's current, I2. The more power the load asks for, the more power the primary side pulls in to provide it. And that is how power gets transferred across that empty gap. It's a beautiful balancing act. Okay, so everything we've talked about up to this point has been a really clean, simple picture. But now it's time to pull back the curtain, because we've been working with a bit of a simplification. Let's get into how this stuff works in the messy, complicated real world. You see, everything we've described so far has been what we'd call an ideal transformer, a perfect, 100% efficient machine where every single bit of energy you put in comes right back out. No waste, no losses. But we all know the real world isn't perfect, right? Nothing is 100% efficient. So what's really going on inside that physical gray box you see on the utility pole? In reality, things get a little messy. For one, energy gets lost. The copper wires themselves have resistance, and they get hot. That's energy literally turning into heat and disappearing. The iron core does the same thing. And that perfect magnetic field we talked about, well, some of it leaks and never quite makes it over to the secondary coil. So how do engineers possibly build anything if reality is this messy? They use this, the equivalent circuit. I know, it looks a lot more complicated, but think of it as a more honest, detailed map of the transformer. Every single one of those real-world imperfections we just mentioned now has its own symbol on this diagram. Let's just break it down real quick. See those R and X components on the far left and far right? Those represent the energy being lost as heat in the copper windings. Now look at that branch in the middle. That models the transformer's core. It accounts for both the magnetizing current and the heat losses that happen right there. So with this map, every real-world flaw has a predictable place. So we've gone from a simple idea to a pretty complex diagram. You might be asking, why does this even matter? Why go through all the trouble? Well, this is the difference between a cool concept in a textbook and a tool that can actually power a city. Here's the bottom line. The simple, ideal model is great for understanding the basic idea. But a practical model, like this equivalent circuit, is what allows an engineer to actually build something that works. It lets them predict exactly how much energy will be lost, how hot it will get, and how it'll perform in the real world. It's what makes the theory useful. So let's just recap the whole journey. First, we learned the transformers have a baseline idle current just to keep their magnetic field alive. Second, when you connect a load, the transformer instantly and automatically draws more power to meet that demand. Third, real-world transformers aren't perfect. They have predictable energy losses. And finally, that complicated-looking equivalent circuit is the essential map that lets us account for those losses and design the reliable technology that powers, well, everything. This whole journey, from a perfect concept to a practical, messy model, that's engineering in a nutshell. It's how we harness complex physics to actually build the world around us. Which, it kind of leaves you with a bigger thought. What other complex realities, in science, in economics, even in our own lives, are we simplifying every day just to get a handle on them? Something to chew on. Thanks for watching.